determine analytically the Laplace transform of the following function. So we have f of t is equal to e to the negative at times sine omega t. So when they say determine analytically, they mean do it using brute force. So plug it into the equation for the Laplace transform and solve it. So recall the equation for the Laplace transform is the integral from 0 to infinity of e to the negative st times f of t dt. So what we'll do is we'll just plug that in, but first we'll go over, first we'll transfer sine into exponential form. So recall that sine omega t is equal to e to the omega I t minus e to the negative omega I t over 2I. So then that gives us, so when we plug that in, we get the integral from 0 to infinity of e to the negative st times e to the negative at times e to the omega it minus e to the negative omega it over 2I dt. So what we can do straight away is we can take the 1 over 2I out. And so the key thing to remember is you always want to have the negative in front of the coefficient of t. So that that way it's a lot easier to manipulate when you plug in infinity after you integrate. So what we're going to have in that case, so by expansion we get e to the negative, then s plus a minus omega I t minus e to the negative s plus a plus omega I t dt. And so now we can just evaluate these integrals on, we can just evaluate the integral straight away. So that gives us 1/2 times negative 1 over s plus a minus omega I plus 1 over s plus a plus omega I. And this has an exponential with some stuff up top, but it's not that important, so I'm not going to rewrite it at the moment. So it's plus. And then that is between 0 and infinity. So when we plug in infinity, it's negative. So when we plug in infinity, because it's a negative exponential, it'll automatically go straight to 0. And then when we plug in 0, it becomes 1. So the exponentials therefore are eliminated. So this leaves us with 1 over 2I times negative 1 over s plus a minus omega I plus 1 over s plus a plus omega I. Yeah. And so now what we're going to do is we are going to combine the fraction so that we can get a common denominator. So the way that we do that is we multiply each one by the other fraction's denominator. So then that gives us this expression. So if you look, the s and a's for the top are going to cancel out. And then that'll leave us with negative 2 omega I as the numerator. And then on the bottom, if we view the s plus a as a single term, then when we expand the bottom, it's just going to result in a difference of squares, which with the i's is just going to end up being an addition of squares. So we get 1 over 2I times negative 2 omega I over s plus a squared plus omega squared, and now we just cancel the I and the 2, leaving us with negative omega over s squared plus omega squared. And this is our answer. Next, we're going to solve differential equations. Pardon me. We're going to actually solve differential equations using the Laplace transforms. So for this, we're not going to do the brute force method of plugging it into the equation. We're just going to go ahead and use identities that we already know. And if you don't know them through practice, you'll just learn what they are, and they'll just the more you practice, the more concrete it'll be. Kind of like identities such as sine of pi over 2, that is 1, etc. Similar to that. Alright, so the first one that we'll deal with is we have the second derivative of x with respect to t plus 2 times the derivative of x with respect to t plus x is equal to 1. And then we have, for initial conditions, x of 0 is equal to x prime of 0 is equal to 0, which simplifies a lot of our problems. So what we do is we'll start off by breaking this up into different parts. So we'll overall take the Laplace transform of the whole thing. But the Laplace transform, as you know from the definition, is an integral, so you can break it up through addition. So what we can do is we can actually take the Laplace transform of the second derivative of x, which I'm just going to write as x prime, x double prime, and then the and 2 is a constant, so it can come out. Okay, so now for the second derivative, it is s squared, and I'll just denote it capital X for the Laplace transform of x, minus s x prime of 0 minus x of 0. No, sorry. Prime goes there. And so for the single derivative, it's s times x minus x of 0. And then for x, it's just x. And this is 1 over s. So, as we can see here, any of the initial conditions go straight to 0. So this results in s squared x 2s, as remember that we still have the 2 here, so we'll just write it there just for clarification, and then x and 1 over s. So now we're going to recombine our differential equation through addition. So we get s squared x plus 2s x plus x is equal to 1 over s. So now a common factor for the left-hand side is the Laplace transform of our function x. So when we factor it out, we get s squared plus 2s plus 1 times x is equal to 1 over s. Now, we can factor this straight away if we want, but it's not necessary to do it at this stage. So what we're going to do is we're going to isolate for x. So we get 1 over s times s plus 1 squared, which is just this function factor. Now, I'm going to go through 2 methods to go through and factor this. You can choose whichever one you like, and I'll briefly explain them before actually going through them. So, for factoring it, we can see that this has 3 possible factors. We have 1 over s, 1 over s plus 1, and then 1 over s plus 1 squared. And so the reason why we differentiate between s plus 1 and s plus 1 squared is A, if we were to expand this, we would get a power of 3, so you want to have 3 separate factors. B, it's because you might not if you don't have that, then you might not actually be able to get a complete solution. And so sometimes one of these will be equal to 0, the coefficient. However, oftentimes one of them has a value such as 1, 1/2, or some numerical value. So it's always important just to remember to have them here. Now this allows us, now this is where I'm going to branch off into the two methods. So the first method is just brute force. What you're going to do is you're going to take the factors that aren't present in the fraction, multiply by the top, and then add all the tops, equated equal to 1, and just brute force using algebra. The second one is using limits. So for the limit one, what we're going to do is for different zeros, so for example here it's 0, here it's -1, we'll actually take the limit of the overall function at that point, removing it. Now, because we have a repeated one here, we won't be able to do the middle factor, so we'll have to only do it for the first and last one, so we'll be able to determine A and C from this, but B we'll have to determine using algebra. So, algebraically all the way through, we get A times S plus 1 squared plus B times S squared plus S, which is S times S plus 1, plus CS. So now when we expand this, we get AS squared plus 2AS plus A plus BS squared plus BS plus CS is equal to 1. So what we're going to do is we're going to isolate for the different powers of S. So for S squared, we get A plus B, and that has to be equal to 0 for the coefficient, because in the coefficient here, we don't have any S squareds. So you could also view this as 0S squared, if that helps. Then for S, we have S times 2A plus B plus C is also equal to 0. And then for 1, we have just A. So we know that A automatically is going to be 1. And then from here, we have B is equal to -A. So we know that B is equal to -1. So for C, what we're going to do is we're going to plug both B and A in, so then we get 2 minus 1 plus B plus C, is equal to 0. So C is also equal to -1. Now, to show how we can get both A and C using limits, what I'll do is I will take 1 over S plus 1. What you do is you have, so A, for example, the 0 for this factor here is 0. So what we're going to do is we're going to take the limit as S goes to 0 of everything except for that factor from the original one. So it's 1 over S plus 1 squared. So when we do that, we get 1 over 1 squared, which is equal to 1. So that's it. And then for C, we get the limit as S goes to -1 of 1 over S. And again, the reason why we didn't do this is because if we were to, we always want to go with the highest power if ever you have repeating factors. And the reason for that is if we were to do this and we were to remove one of the S plus 1s, there would still be an S plus 1 in the denominator, resulting in 0 in the denominator, which is never fun to play around with. So, we have -1 in that, which gives us -1, which is our C. And so from here we can solve for our B, just say using this equation here. And so now if we're actually converting it back, what we're going to do is we're going to put the coefficients back into the factorized form and then simplify. So when we do that, we get the inverse Laplace transform of x is equal to the inverse Laplace transform of 1 over s minus 1 over s plus 1 minus 1 over s plus 1 squared. And so now, this equates to x of t is equal to 1 minus e to the negative t minus e to the negative t times t. And that that is how you solve differential equations using Laplace transforms. So now just another one, just to confirm our knowledge of this. A key thing to remember regarding this is if ever you see a differential equation that looks absolutely baffling to you upon inspection, you just don't know what to do at all, normally the Laplace transform will be able to simplify the actual solving process. And oftentimes for non-homogeneous differential equations, so where it isn't equal to 0 on the opposite side of the differentials, it's key to remember to use Laplace transforms because they'll simplify everything. So now we have the second derivative of y with respect to t minus 3 is equal to 0. And again, initial conditions are y of 0 is equal to y prime of 0 is equal to 0. So now what we're going to do is we're going to apply the Laplace transform. So recall the Laplace transform of y double prime is equal to s squared y minus s y of 0 minus y prime of 0. And again, these two are both 0. And then the Laplace transform of 3 is equal to 3 over s. And Laplace transform of 0 is just equal to 0. So we get s squared y minus 3s is equal to 0. So what we're going to do is we're going to multiply everything by s. So we get s cubed y, because clearly s can't be 0, so we don't have to worry about it as it's already in the denominator. So we get s cubed y minus 3 is equal to 0. So then y is equal to 3 over s cubed, and then we take the inverse Laplace transform of that. And that gives us y of t is equal to t cubed over t squared over 2 times 3. And again, the reason where the 2 came from is because of the definition for polynomials. So say you have Tn, the Laplace transform of that is going to be n factorial over s to the n plus 1. Sorry, s. Yeah. Sorry, there's no 3 there. And so again, the 2 just comes from the 3 factorial. That is seeing as to how it wasn't 6, it was 3. And so that is the solution to our function. Okay. I move on to the other side of the book. Okay, so now for finding inverses of the Laplace transform. So we've already done this twice so far, so you should be starting to see how different kinds of functions, how their Laplace transforms work. So for this one, so we have 1 over s squared plus 2s plus 10. So the key thing to always remember is you always want to take the bottom and try to make it into some sort of multiples of squares, because then it's a lot easier to deal with. So what we can do here, or addition, sorry, of squares. So we can take s squared plus 2s plus 1 plus 9, where the 1 and the 9 came from 10. And if you look, this part here can be factored to 1 plus s squared. Or yes, 1 plus s squared, or s plus 1. And this can be factored to 3 squared, or minus 3i squared. So when we do that, sorry?
Big bug.
Where?
Kill it. Oh, you're gonna crush.
Yeah, it crushed. Anyway. So, yeah, no worries. So if you look, we can simplify this expression by just looking for key things to be s plus 1 squared minus 3i squared. So then this leads us to the following factors. So we have a over s plus 1 minus 3i plus b over s plus 1 plus 3i. And so since there's no real part to the solution, we're going to have to solve it using algebra. But since there's only two, it's not that hard. Normally when you have 5 different factors, that's when you use the limit method, because it would save much more time than actually going through and doing the algebra for 5 separate equations and 5 separate unknowns. So what we get is a times s plus 1 plus 3i plus b times s plus 1 minus 3i is equal to 1. So then we get s times so we get s times a plus b plus 1 times a plus b, and then we have I times 3i a minus b. And this is equal to 1. Let's see, off the bat, we know that this is gonna have to be 0. So a is equal to negative b, which automatically means that this is 0. Now don't get alarmed just yet, because we still have the 3i, right? So we have 3i of a minus b is equal to 1, right? Because of the a plus b is equal to 0, a equals negative b, so both of these are gone. So we're left with this. And so now what we're going to do is we're going to divide both sides by 3i. So, and we'll plug in negative a for b, so we get 2a. So we get 2a is equal to 1 over 3i. Yet a is equal to 1 over 6i. And then we get from here, b is equal to negative 1 over 6i. So now we can solve it. And we have, I'm just going to put 1 over 6i outside. It's going to be a lot easier. So the inverse Laplace transform of 1 over s plus 1 minus 3i plus 1 over s plus 1 plus 3i. And so now the solution to this is e to the, let's see, that would be, so if we were to put negatives through here, just to simplify things a little bit. So this is what the coefficient for the exponential is going to be. So we get 1 over 6i times e to the negative 1 plus 3i t plus e to the negative 1 minus 3i t. And so now what we can actually do is we can factor out an e to the negative t. So do that over here. So we get 1 over 3i, and You'll understand why I'm taking the 2 out in just a second. E to the negative t. And then we have e to the 3it plus e to the negative 3it over 2. And so the 2 came from the 6i. And so now what we can do is, this is the definition for cos of 3t. So now we have 1 over 3i e to the negative t cos 3t. And this is our solution. Now I'm fairly certain that profs would be satisfied with this. I just like making things look neat and tidy. So. Are you guys done with this board?
I'm done the first problem.
Okay, so I can erase from here over.
Caleb,
Still good from here over there, Michelle?
Yeah.
What do you guys think of that little limit chart for factor?
I'm not. Okay, I'm gonna be honest. I was just trying to like copy down what you were saying. I wasn't really paying attention.
Okay, fair enough. Well, again, if you guys have any questions, feel free to stop me. I tend to think faster than I write and write faster than other people.
Well, like I said, like I didn't really go back to the problem, so I still have to write down everything that we covered last time.
Okay, fair enough.
So, sorry.
It's okay.
It's good to be for me.
Yeah.
So what did you do to
So what? From here to here? Or?
Oh yeah, because you wanted to take the minus to make it easier to fit the transfer.
Exactly, yeah, that's all. Alright, over here? Or?
I'm still right there, yeah.
Oh, here?
Yeah.
Yeah, it's easier to factor it if you look at difference of squares versus when you have plus, like say a squared plus b squared, most people, when they look at that, they're like, it's unfactorable. But it can be factorized, just you have to go into the realm of complex numbers, which not everybody enjoys. Understandably, I mean, complex numbers are called the complex numbers for a reason. Friggin' complicated sometimes. Anyway, so moving on. 3b, and we have s over s squared plus 4s plus 4. Now the bottom can easily be factored to s plus 2 squared. And so now what we're going to do is we're going to factor it into a over, actually it works, a plus 2, so a over s plus 2, sorry, plus b over s plus 2, no, this is not going to work, damn it. Oh, maybe. Yes, well, yes, haha, because it's the s. So what we're going to do is we're going to take a and multiply it by s plus 2, and then we have b. Sorry, this should be squared. So we have a times s plus 2 plus b is equal to s. So we have s times a is equal to s, so a is equal to 1. I really like having a equal to 1 for some reason. Not in that problem, but generally. And then we have 2a plus b is equal to 0. And we know that a is equal to 1, so we know that b is equal to negative 2. So, this leaves us the following fractions of 1 over s plus 2 minus 2 over s plus 2 squared. So now we'll do the Laplace transform. And one thing to keep in mind, if you have, say, if you have the same addition to all s's, then what you can do is you can actually have, you can actually factor in an e to the negative whatever straight away. So in this case, it would be e to the negative 2t outside. And what you do is you convert all of those s plus 2's straight to s's. So then you get 1 over s minus 2 over s squared. And so this just equates to e to the t times 1 minus 2t, I believe. Does that seem right? From here to here? Just double check.
Okay, wait. So we did. The first one is, so if you do the Laplace transform of 1 over s, it's 1, yeah?
Yeah.
And then 2t, yeah.
Okay.
According to me, anyways, Caitlin.
Sorry. And there we go. That is our solution for B. And just let me know when you're done with A.
You know what? I can probably write these out mostly on my own. Like that one looks pretty simple. I'll probably figure it out on my own.
Okay.
I just want to write this down. There.
Here?
Okay, so you took out 3i, you factorized 3i.
Yeah.
And then, so you said that 3i a minus b has to be equal to 1?
Yeah.
Why?
Because from here, we saw that a plus b is equal to 0.
Yeah.
So then both of these terms went to 0, meaning that this was the only term left to equate to I.
Why did that second term go to 0?
This one here,
Yeah. Why didn't that one get equal to 1?
a plus b, a plus b. A plus b is 0, so yeah. Because we had 3 terms here, right?
A has to be equal to minus b. Okay. I don't see how you can just like assume that. Like I know you're right. It's just I'm trying to think like.
I know normally it's the 1 that is equal to the 1. This time it's
Yeah.
a bit of a curveball. Yeah, essentially what it is as long as you have a constant coefficient, which technically this is a constant coefficient, right? I is as much of a constant as pi or er, or square root of 2 or whatever. But yeah, normally it's about 85 to 90% of the time this will be the term that you're looking at. But every 15...
Is it because s can't be equal to 0? Like,
yeah.
Like the term is equal to 0, but s can't be equal to 0, so therefore a plus b has to be equal to 0.
Yeah, like we're essentially trying to solve for
Okay.
the coefficients on everything.
That's right. Okay, that's fine.
Because it's another way to look at it is 0x, right?
Mm-hmm.
So
Yeah. Okay, that makes sense. Let me just write that out real quick.
okay. Yeah, because then whatever the coefficient on 1 would be would also be the coefficient on s. Since we didn't have an s before, right?
Yeah.
It's pretty much factor solve.
And if ever I have real trouble with that, I can go back and see that.
Alrighty. So,
Systems of differential equations.
spooky stuff.
Okay, I think I remember. Yeah, so if you need 2 equations to solve 2 unknowns, and they give you 2 initial conditions.
Yeah.
So it's good.
Yeah.
So let me just write these down.
Is it okay if I erase what's on the board right now? You know what they need to come up with? An Etch-a-Sketch blackboard. So you just like press a button, it vibrates and clears itself. How much money would be made off of that for universities? And you know, instead of like, especially in the universities where they have like 8 blackboards, instead of like somebody just sitting there erasing all that, you just like press a button, done.
That person would be the happiest person in the world.
Oh yeah. Mind you, you'd be getting rid of someone's job. Like, you know, if someone were paid to clear blackboards all day, it'd be the shittiest job in the world.
Janitors.
Probably get asthma after like a month.
Okay, so this is solvable.
Which one?
And how?
Oh,
Once you jog my memory, I should get this.
for 4? Or
Mm-hmm.
okay. So So for 4a, this is systems of differential equations, which is even more fun than we've already had regarding Laplace transforms. So we have x prime of t plus y of t is equal to sine of t. Thank you. And then we have x of t minus y prime of t is equal to 0. Where we have x of 0 is equal to 1, and y of 0 is equal to 0. So what we're going to do is we're going to we're going to take the Laplace transform of both the equations, and then we're just going to solve for one in terms of the other, and then put it in, solve it, and then transfer it back to solve the other equation, and then it'll be good. Sounds a little funky when I explain it like that, but we'll see how it goes. Anyway, so recall just this. I'm going to have so we have x minus 1 plus y is equal to 1 over s squared plus 1. And then we have x minus sy minus 0 is equal to 0. So, I don't know about you guys, but I think this is going to be easier to turn around regarding substitution. So using this one, we get x is equal to sy, right? And then what we'll do is for each x in here, we're going to plug in sy. So then we get s times sy minus 1 plus y is equal to 1 over s squared plus 1. And this is going to become quite interesting.
Ooh, wait.
Yeah.
How did you get x is equal to sy? Oh, you just... Oh, okay, I see. You took the second equation.
Yeah. Oh, it'd be easier than this and getting all sorts of crazy stuff.
Okay.
So we get s squared plus 1 times y is equal to y, or 1 over s squared plus 1 plus 1. Right? So we bring the 1 over, and then we get s squared y plus y, so then we can factor the y out. And then we get this. Good with that so far? And so then we get y is equal to 1 over s squared plus 1 squared plus 1 over s squared plus 1. And so recall that x is equal to s times y. So then what we do for x is we just multiply everything by s. Okay, so for finding Laplace transform, or the inverse Laplace transform, of y, we're going to get y of t is equal to, now we have 1 over s squared plus 1. So recall that that is going to give us sine of t right off the bat. And now we need to find the inverse Laplace transform of 1 over s squared plus 1 squared. Now this is where things get a little bit complicated because it's not a very easy function to deal with when it comes to factoring and things like that. So to factor it, what we're going to do is we're going to have 1 over s squared plus 1 all squared is equal to a over s squared plus 1 plus b over s squared plus 1 squared. No. Now for 1 over s squared plus 1 squared, you can likely look that up in a table that you will be given for tests. That is going to give you 1/2 times sine of t minus t cos t. Now, I know that I didn't go through to actually solve it, but to go through and solve it would take significantly longer than I have time available right now to give. So, for the time being, that is the answer. So, for y anyway, y of t is equal to sine of t plus 1/2 sine of t minus t cos of t, which could further be simplified as 3 over 2 sine of t minus t over 2 cos of t. Now for x, we have so this is going to yield us cos of x, or cos of t, sorry. So we don't have to worry about that anymore. As for this one here, we can use a little principle. Now I'm just going to jog my memory, make sure that I'm not saying anything that's incorrect. So, what it's going to yield is it's going to yield 1 over 2 t sine t. And the way that we go through to find that is we take, so if you look, and say we were to multiply this by a over a, right? Now this looks very, very, very familiar. Right? It's very, very familiar to the derivative of this. And it happens to be an identity that the inverse Laplace transform of f of s, the derivative of f of s, sorry, is equal to t times f of t. Okay? With me so far? So now what we're going to do is we're going to determine what a is, which is negative 2 because of the way that numbers play out. So this is going to become negative 2 over negative 2. So we're going to use this here to get t times the derivative of this. So we're going to have negative 1/2 of the inverse of 1 over s squared plus 1, which is equal to, and then we automatically have t because of the multiplication that we did, times, and we already know from here that it's just sine of t. And again, over negative 2. So our answer here is going to be minus 1 minus t over 2 sine of t. And that is our x. And that is how you solve systems of differential equations using Laplace transforms. And now, for the last question, we're going to get into the final value theorem, which is where if a function, as it approaches infinity, converges at a finite point, you'll be able to actually use Laplace transforms to approximate that point instead of using conventional limits, which sometimes can get a little bit messy. So for that, just let me erase the board real quick. So the equation for that is if the limit as t goes to infinity of f of t equals finite, i.e. it has an actual concrete numerical value, then the limit as t goes to infinity of f of t is equal to the limit as s goes to 0 of s f of s. With me so far? Good. So now what we're going to do is we're going to look at two problems. So first one being y. So for A, we have y of t is equal to 2e to negative 0.1 t. So we can see upon inspection that as t tends to infinity, this is going to be equal to 0 just because of the properties of the exponential function. However, what we're going to do is we're going to go through and actually use the final value theorem to evaluate the limit. So we have, the Laplace transform of this is going to be 2 over s plus 0.1, right? And so now what we're going to do is we're going to multiply by s. Or sorry, this is going to tend to 0. Interesting. So what we'll do is multiply by s, and then we'll take the limit as s tends to 0. Right? And so now as s tends to 0, the denominator becomes 0.1, while the numerator becomes 0. And so now we have 0 over some constant, which is equal to 0. We don't have to worry about 0 over 0, so we're good to go. And so now that gives us 0 over 0.1 is equal to 0. Therefore, the limit as t tends to infinity of 2e to the negative 0.1 t is equal to 0. Now for the second one, we have two parts. We don't just have the exponential, we have a constant as well. So for x of t and b, that is equal to 1 minus 5 e to the negative 0.5 t. And so now what we're going to do with that is, same thing, we're going to find the Laplace transform. So x is equal to 1 over s minus 5 over s plus 0.5. And then we'll multiply by s. So then that gives us 1 minus 5s over s plus 0.5. And then we'll take the limit as s tends to 0 of 1 minus 5s over s plus 0.5. Now when s tends to 0 here, doesn't affect the 1. Sorry, it should be there. So it doesn't affect the 1 whatsoever. In this case, for the fraction, the same thing happens over here. We get 0 plus 0.5, so we have a numerator, we have a numerical value in the denominator, so we're good to go. And the numerator becomes 0, so we get 0 over 0.5, and so then that becomes 0. So then we get 1 minus 0, which is equal to 1, which again, upon inspection, we could have seen ahead of time. So therefore, the limit as t tends to infinity of 1 minus 5e to the negative 0.5 t is equal to 1. Because again, 1 is just a constant straight flat line that intersects at y is equal to 1. And this is a negative exponential, so as t tends to infinity, it will gradually approach 0. And that is the problem set for tonight. So again, if you have any questions, you can contact me at my phone number, which is 613-899-9042, or my email, which is s26034@rmc.ca. If you wish to schedule private tutoring, so one-on-one, I'm open to do that. Just let me know what works for you, and I'll try to work with that. And again, I'll be having tutorials for 103 or pre-calculus Sunday nights from 8 to 10, Gerard 133, and third year calculus, which is MA 315, 325, and 328, Thursday nights from 8 to 10 at Gerard 133 as well. All right, thank you.